Right now, as you watch this, a rock from another star system could be cutting through our solar system at 20 to 60 kilometers per second, and we could still lose it after just a few nights of data. What if I told you 3I Atlas is gone doesn't mean it vanished? It can mean something way more embarrassing. We literally can't predict where to point the telescope anymore. Stay with me, because by the end of this video, you'll understand the 3 reasons an interstellar candidate disappears, and the one twist that turns a cosmic mystery into a simple human mistake. It feels impossible. The universe delivers a visitor from another star, something we may never see again, and then it's just gone. But stack these impossible facts and it becomes painfully believable. The object can be so faint, it's basically a whisper in the data, especially if it's small, dark, or moving into a crowded star field. If you only observe it for a short time, hours to a couple nights, your orbit is a best guess, not a lock. And that guess can balloon into a giant uncertainty region. And some objects don't move like clean textbook asteroids. Outgassing, fragmentation, even subtle forces can turn "we know where it'll be tomorrow" into "it could be anywhere in this whole patch of sky." So what happened with 3I Atlas? Did it fade? Did the math fall apart? Or did it physically change in a way that made the original orbit wrong? To get this, you need the normal discovery pipeline, because the weirdness comes from how astronomy actually works. Surveys like Atlas take repeated wide-field images and look for dots that move. Most moving dots are normal: near-Earth asteroids, main-belt asteroids, comets, satellites, old rocket bodies. The moment something looks unusual, follow-up begins. More telescopes, more measurements, better orbit fits. The clearinghouse for this is the Minor Planet Center, which collects observations and publishes solutions. Interstellar candidates are special for one reason: their path is unbound. In simple terms, that means the orbit isn't an ellipse around the sun. It's a hyperbola. It came from outside and will leave. People often summarize that with eccentricity E1. But the grown-up version is this: you want the barycentric orbit relative to the solar system's center of mass, not just a quick first-pass heliocentric fit. Early fits can lie. This is where things get strange, because an orbit is not a photograph. It's a mathematical story inferred from a handful of dots. If you've only seen an object briefly, you're fitting multiple unknowns from limited data: distance, velocity, direction, plus measurement noise. Many different orbits can explain the same short arc. That's why your predicted position tomorrow isn't a dot, it's a region. Wait longer, and that region grows into a cone that can be huge. And here's the simplest way to picture it. It's like trying to predict the exact location of a speeding car tomorrow after you only saw it for 1 second through fog. You're not getting a single answer. You're getting a widening set of possibilities. So when people say, "it's gone," it often means something painfully unromantic. We don't know where to point the telescope with high confidence anymore. Subscribe if you like space mysteries with real receipts, because the next part is the exact detective checklist astronomers run when something vanishes: fading, orbit uncertainty, or physical change. And then the twist that can make a third interstellar object turn into space junk. Stay with me here. Let's run the case like detectives, because we've seen versions of this movie before. In 2017, Oumuamua was discovered and immediately became a race against time. It was fading, moving fast, and every day made follow-up harder. In 2019, 2I Borisov was discovered, and this one looked like a comet: gas and dust you could track longer. Those 2 objects taught astronomers the same lesson from 2 different angles. The first days are everything. Miss the follow-up window, and you don't just miss a cool photo, you lose your ability to predict, refine, and understand. Now put yourself in a 2026-style reality. Surveys are faster, alerts are more automated, and the sky is more crowded with data than ever. That sounds like it should make losing objects impossible, but it creates a new problem: more detections right at the edge of visibility and more opportunities for confusion. 3I Atlas is gone can actually mean 3 totally different stories: one boring, one scary, and one humiliating. Here's the main explanation. There are three realistic ways an interstellar candidate can disappear. First, it faded below detection. You might be thinking, if it's real, why can't we just see it again? Because brightness is a trap. It depends on distance, illumination angle, reflectivity, and activity. A small, dark object can drop below survey limits quickly. Even worse, it can drift into a crowded background where separating it from stars becomes a nightmare. The object didn't vanish. It just became invisible to our current tools. Second, the orbit uncertainty exploded. This is the most common gone story. With a short observation arc, tomorrow's predicted position is a region. Next week's is bigger. Soon it's a patch of sky so large that searching it is like looking for one specific grain of sand by staring at the entire beach. Here's where it gets crazy. You can have good measurements and still lose it because the math was under-constrained. One more night of data might have saved it. One missed night, clouds, moonlight, scheduling, and the cone balloons. Third, it physically changed or moved non-gravitationally. Comets can fragment, dust can cloak the nucleus, outgassing can produce a tiny thrust that adds up over time. Oumuamua famously showed non-gravitational acceleration that triggered serious debate about the cause. If 3I Atlas was active or fragile, it could have dimmed, split into pieces, or deviated from a simple gravity-only path. So yes, the satisfying answer is, gone usually means too faint, too uncertain, or not behaving like a simple rock. But it raises a bigger question. If interstellar objects are this easy to lose, how many fly through unnoticed every year? Just when you think you've solved it, here's the twist. Sometimes the object isn't gone. Sometimes it was never a true 3I in the first place. At the detection limit, misidentification is a real threat. A faint dot can be a satellite, a rocket body, or an imaging artifact. If follow-up fails, the candidate collapses. That's not scandal. It's quality control. Astronomy is ruthless because it has to be. And the second twist is even more subtle. Early orbit solutions can look hyperbolic simply because the dataset is short. Add more observations, and the orbit can swing. The real test is the barycentric orbit and long-term behavior, not a first-pass E greater than 1 headline. So the debate becomes, did it truly go missing, or did it never graduate from candidate to confirmed interstellar object? That's why people online can watch the same story and walk away with opposite conclusions. I genuinely want to know what you think happened. If 3I Atlas is gone, what's the most likely explanation? A. It faded and we can't see it now. B. The uncertainty cone exploded and we lost the track. C. It fragmented or was misidentified from the start. Comment A, B, or C, and tell me what evidence would convince you. More detections, spectroscopy, or a stable orbit fit. Because this matters. Interstellar objects are free samples from other planetary systems. Physical evidence of how other stars build planets. Chemistry, dust, ice, rock. That's not sci-fi, that's comparative planetology. And the same tracking tech is also planetary defense tech. Better surveys, faster follow-up, better orbit fitting. Those aren't just cool astronomy. They're part of Earth's warning system. In the 2026 era, the big shift is scale. More wide-field surveys, more automation, more detections near the limit. That means more discoveries, but also more lost object moments, unless the follow-up network becomes faster and smarter. The hopeful part is we are improving the system. Alerts are faster, orbit codes are better, and telescope coordination is becoming more global. Every time we lose an object, we learn how not to lose the next one. But this isn't the only mystery hiding in plain sight. Next, I'll show you how astronomers compute an orbit from just a few dots, how to tell a true interstellar hyperbola from an early data illusion, and the wild question, could we ever launch fast enough to intercept the next visitor? Thanks for watching. Space doesn't need to hide things from us. Sometimes it just makes them faint, fast, and unforgiving. Stay curious, and see you in the next one.